presentation. Tonight, I think is an interesting presentation. We'll see how it goes. I don't know how many of you know me or have seen me talk before, but we'll do a demonstration or two. And I don't like rehearse any of this stuff, so we're just gonna see what happens. I am Dave. It's a pleasure to meet you. I have been teaching for SANS since 1999. So it's last century for me. It's a long time. And in that time, I've been involved in a lot of different classes that SANS offers. I've actually authored, I don't even know, like lots of classes in that time. These days, in SANS world, I am the Dean of Faculty for the STI College, so the Master's Degree Granting Organization, the graduate certificates, that's where I am. I am also the owner and author of the 503. Has anyone taken 503 this week? Yeah. Oh, but you've taken it before. Okay, so 503, which is, tell me if I'm lying, the best SANS class ever, and everything you ever needed to know about network monitoring, which is actually super important because you know what? We say that data drives the world today, right? It does. But how do you get that data? It's all communication, man. Sure, you can throw things on a USB stick. I actually spent my afternoon. I had 6 gigs of files I needed on that laptop. It's actually that laptop over there. And I had it on this laptop over here. And do you know I could not find someone with a USB stick I could put that data on? So how did I get it there? Network. I mean, it's how we move everything. So network is pretty important stuff, but that's not what we're here for. I am also the author of the data science, and I'm sorry about this name. I'm not even going to get it right. Data science, machine learning, and AI, blah, 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 applied for cybersecurity. And this is, I'm sorry, it is absolutely some of the SANS marketing folks who are just like trying to get every search engine optimization word they can in there. But it's about how you apply that to information security. I, in my day job, am the chief of operations for a managed security organization where we do the stuff we teach in 503 for large corporations. Not a lot of corporations. We are sort of the last stop people come to when they've been through companies, they've bought all the products, they've tried to do it themselves, and they still have issues. And they finally say, we need someone who knows what they're doing. So they end up with us. I'm also a director with a UK-based company that does a lot of government contracting with some stuff in the UK. So other stuff, not network monitoring stuff, just other stuff. I am also sort of the AI machine learning evangelist in my organization, even though the chief of operations, and kind of lead that research function. And I feel like I sort of do that at SANS too. Though, I mean, other people think it's cool and think it's useful. I kind of lead that stuff. And I want to introduce our topic this evening in terms of threat hunting. Because you know what? It is the hotness right now, right? That's true. That's completely fair. And I'm not trying to ride on that. And as those of you who have taken 503 before, it doesn't actually matter if you took that last week, last month, last year, last decade. That class has been teaching threat hunting since the 90s. It's just like how we do the threat hunting that's changed. And as those of you who have been, who's been in the industry for more than 10 years, if you've been in the industry more than 10 years, I know you've had this happen. You read some new blog entry, you hear some new podcast, you look at some video, you go to some conference, and they tell you about this new amazing thing they're doing, the new Lockheed Martin. What's it called? Well, it's not called Thingamabob. What's the cyber kill chain? And you're like, whoo, that sounds important. Let me learn about that. And you look at it and you say, there's nothing new in that. Or you hear, zero trust. We need zero trust. Well, that sounds important. What's that mean? That means you can't trust anything. So you have to harden it. And you say, wait, isn't that defense in depth? So we just add like new words to things. I know, it's like not popular to say, but that's the truth of things. So threat hunting's been around a long time, but it's the current hotness as is AI and machine learning. But I fear something bad is going to happen in the AI world in the next few years. I'll tell you what that is soon, so don't worry. Anyway, when the internet dinosaurs roamed the earth, we had to find threats. And the threats we dealt with were things like viruses, which were kind of new. We had Cookie Monster and Jerusalem A and B. And I mean, that's like the early 90s. That was the dawn of the internet, which was actually a little older than that. And it was the days when, I love when I can't remember who this was they were talking about, when the internet was created in like, I think they said like 1998. I'm like, no, it was around a lot longer than that. That's just when web browsers came around. We had a lot of publicly accessible systems. We had a lot of stuff with no passwords on them. We actually had people actively not setting passwords, like Richard Stallman, who's well known from Free Software Foundation. He, for many years, it was well known, you were invited, if you would like to log into his MIT account, his username is RMS and his password is RMS, and he would publish it because he was all about open. I don't think he does that particular thing anymore. He still doesn't wear shoes as far as I know, but he does have some other oddities. Anyway, things have changed. In those days, though, when it came to anomaly detection, the way we approached it, and by anomaly detection, by the way, I mean threat hunting. Because we call it threat hunting today, but it's anomaly detection. I'm looking for what's the weird stuff? What's the thing I don't expect to see? Because that could be a threat. And the way we did the anomaly detection is we would create filters that said, here's what I think I should have. Show me everything that's not that. Which I know you hear that and you're like, oh, that sounds like that's like a modern approach for things. Yeah, we were doing that in the mid-90s. But then we went into this period of time where we tried to automate all the things. And that's a good thing. But we went from trying to automate what humans do, anomaly detection, and humans are actually really good at that. And Gartner started to say, everybody needs this security stuff. So what do the security vendors say? We need to sell that stuff. What do we know how to do now? We know how to detect viruses. And the way we do that is we look for known signatures. We see if that thing is present. If it is, that's bad. And what we need to add into that is the ability to do it on networks and bigger things than files and behaviors, and that's what we need. So let's find out how people do anomaly detection. And when you talk to anomaly detectors from the 90s, they explain to you what you need is someone with deep domain knowledge who can look at the thing and tell you if it's weird. And the security vendors say, well, that's really cool, but how do I write that? That's pretty hard. However, I have a thing called a virus scanner, and that uses signatures of known bad things. So what if I just took that and scaled it? Because now I don't have to train anybody, and I can sell that product. And I can even sell you updates to signatures, which thankfully we don't do anymore, at least to some degree. You need to have like the ongoing renewal and stuff, but it used to be more costly. But that stuff hasn't really changed much in 20 years. How are we detecting threats today? Because what I've just described to you is the transition from 98 to 2000. How are we detecting threats today? Are you running antivirus tools on your network? How are you detecting network attacks? Is it still looking for signatures of known attacks occurring on our technology hasn't really changed much. Oh, but wait, we have SIMs. Oh, okay. So you're shoving everything into the SIM. And we went from the days of everyone wanted skinny logs, and now we've gone entirely the other way. This is like a weight loss system, right? First they tell me eat no fat, and then they tell me just eat fat. You just need fat. So we go from skinny logs, and now what are we doing? We're enriching our logs. And I shove it all into a SIM, and I feel so bad for the SIM guys. Because your life, if you're the SIM person, you spend your life, people don't understand what you do. I just shove the logs at you. You need now to interpret that in some way and create something in whatever language that thing uses to do a correlation and tell me that there's an important thing occurring. Because unfortunately, when we're enriching our logs and shoving everything into it, we're not sending into it, oh, hey, by the way, the thing someone is doing to me right now is probably a bad thing. Instead, we're just sending all of the data and letting the SIM guy sort that out. There's actually an example of this that I think is a phenomenal one. I mean, a phenomenally bad one. It's Yahoo. Now, if you're a Yahoo employee, do not identify yourself, okay? So the Yahoo breach, and I don't remember the numbers here, but I mean, they're huge. Was it over 1 billion? 700 million? I mean, it's a huge number. Look around the room, 1 in every 6 humans. And if you are in a developed country, it's bigger than that. It's a lot of personal information compromised. Now, okay, everybody is going to get compromised. I know that's a terrible thing to hear at a security conference, but it's true, right? That's the reality. That's zero trust. It's going to happen to me. Well, with Yahoo, it happens, and they don't really, talk about it because there's some dysfunction in the organization between security and management, and just okay. So there's some initial disclosure, and they're in the middle of, unfortunately for Yahoo, they're in the middle of trying to sell themselves. And then after a little bit of time, they have to come out and say, so we were breached 2 years ago, okay, and now we've done a little work and we've realized it's probably more like 4 years ago. What does that have to do with a SIM? Well, I want you to think about what that means. And it is an impressive thing. What that tells me is that whoever was handling that incident could go to Yahoo and they had logs, probably very rich logs, going back more than 4 years from everything. And they were able to reconstruct approximately what happened. And we never did identify who the actors were, but I mean, that is some log retention. It's a shame no one was looking at the logs for 4 years, but I mean, we had the log retention. They've got the SIM, but I don't know what the anomaly looks like until I see an anomaly. What's normal for me is really, really hard, but we're doing it all in about the same way. Now, every vendor out there is telling you, we need to have, and not only do we need to have, but we provide you real-time threat defense. We had firewalls. Then we added a cool new thing called an IPS. And then we said, oh, why don't we make the IPS a firewall? Well, it actually was that to start with, but let's give it another name because IDS is not cool anymore. It's now a next generation firewall. And has virus scanning in it and other, and I can charge a license fee for every one of those things you want to turn on. It's great. So that's where we are today, but how are they working? I'm looking for known attacks. In fact, when you look at these things, what they tell you, it's actually really interesting when you read marketing material critically. So as you're walking through the airport, because we always advertise Barracuda networks and airports and stuff like that, because that's where the network engineers go to decide what hardware to buy, right? Who are we advertising to? The executives who's walking through the airport saying, stops all the attacks. I want that. Why don't we have one of those? But when you read it more closely, they don't say we block all attacks. They say we block all known attacks. Well, that's easy. Because if you know what the attack is, you just write a rule that says you can't do that anymore, right? What's way harder is how do you block the attack you don't know what it is? Now, if you're here, none of this is a surprise to you because you are probably a person who you've got the security tools, you've done the training, you've got the vendors assisting you, and there's consultants in there. But besides all of those things, you just know there's other stuff happening and nothing is telling you about it. In fact, some of you are people who look at your monitoring tool and it has no alerts in it, and you're like, oh, there's something really wrong. I just know there's something happening it's not telling me about. And I got a quote here on the bottom. What you know, you can't explain, but you feel it. You feel it constantly that there's something wrong with the, we'll say the network. You don't know what it is, but it's there. Like a splinter in your mind driving you mad. Of course, what's this from? This is from the Matrix, right? This is the Matrix. And that's how we are with threats. We just know it's there. How do we find those things? What am I selling to you tonight? Nothing. Did you go to any vendor lunch and learns? Now, I'm not, please, I don't mean this as a joke. It is not a joke. I'm genuinely interested because I just don't have the time for them. Did you hear anything or see anything that you're like, ooh, I need that? It's okay if you say no. Someone in my class today, they said something really funny. I think it was today. I asked about which one they went to, and he said, well, I mean, they didn't really articulate well what they were selling me, but I heard a lot about this other thing. And I was just imagining the marketing director who's hearing about this lunch and learn they sponsored, and nobody knows what they're selling. So that's not good. But I'm not selling you anything, at least not a product. I've got no product to sell. I am in this space, but we do not sell products. And I'm also not selling you my service, so don't ask for that either. We build these things to use with our customers. And I'm happy to tell you about how some of the things work. So I want to give you some real practical things you can do with machine learning and AI. I hope you are going to understand when I tell you that I cannot go into great depth into how to do these things in an hour and a half. Okay, is that fair? Because there is a lot of math and other kinds of stuff that underlies all this. There's a lot of coding and stuff, but I'm happy to share that stuff. In fact, I do share it. I've got a pointer to this at the end. There is a bi-weekly, which is one of those confusing words. When is that? So semi-annual, that's easy. That's twice a year, right? Biannual, is that twice a year or every 2 years? Bi-weekly is like this. This is every 2 weeks. About every 2 weeks, I do a live stream on Fridays at noon, which I don't know why this is, but apparently Friday at noon, people like watching webcasts. So I do a live stream then. I think what it is that you are far enough along in the week that you're just exhausted. You want the week to be over and you're very happy to watch videos. I think that's what it is. So I do a live stream that's usually about applied data science and machine learning. It is free, of course. It's on YouTube and LinkedIn, which I affectionately call Dave's Python Fails, because you get to see me do some stream of consciousness Python stuff, and it half the time doesn't work, but in the end, we get something useful. So you can hear about that stuff there. And I always say, if you have a thing you want me to talk about or show you how to do, please let me know. Because believe it or not, doing a live stream every 2 weeks, it doesn't feel like a lot, but coming up with something to talk about once every 2 weeks is a little bit challenging. Because one of the things I'm trying hard not to do is to teach my entire class over the live stream, because that's a little self-defeating, right? But I'm happy to talk about whatever you need. So there's a resource. Well, I'm happy to talk about this stuff. So let me give you a few examples. Let's give you one to start with using NetFlow. And by the way, not only am I not selling you a product, the things I'm going to tell you how to do tonight, there is nothing you need to buy. There is no one you need to hire. You already have everything you need to do this, except perhaps for the knowledge of how to apply it. That's the only thing that might be missing. NetFlow. Now, 503 fans and people who are doing the, what is it, the security operations and the, what's the 511 class? I don't remember the name of that. The continuous monitoring or whatever that's called. NetFlow is not an unfamiliar thing there. NetFlow is a thing you probably already paid for that you are probably not using. Or if you are using it, what you're using it for is to create a pretty picture. What's going on over here? Hey, what are you doing there? Okay, we might have demonstration problems later because it's reconnecting to my laptop. You are probably using it to paint some dashboard that people can look at so you can point and say, see, the network's up. But no one's really using it for a lot. And it is absolutely amazing threat hunting material. because it is metadata information about every single connection that has occurred. I'm going to say on your network, but I mean, it does depend how you instrument it. Every enterprise router, switch, intrusion detection, firewall, every one of them supports it out of the box. Although some vendors like Cisco like to charge you extra money to enable it. But with that turned on, I now have a record of everything that happens on my network. I don't have the content of the packets or of the connections. The content is what your monitoring tools use, your signature-based things, how we do our detection. So it doesn't have any of that in it, which is why most people don't bother with it. But it has a record of every connection. Who talked to whom and when and how many bytes and which way did it go and how many packets were there, everything. Think about that from an incident response point of view for just a moment. You discover a compromised machine on your network. You now begin performing incident response. You don't yet know what happened. You begin doing incident response and you are able to narrow that down, and I can tell you, here is the day when that thing was compromised. Here's when it was last good. I know at this point it was compromised. I don't yet know how, but I know that's when it happened. That's when it went bad. Using my NetFlow data, I can say, well, did that thing initiate any conversations with anything in my enterprise after that date? I don't have any of the content, but I know everyone it talked to. So if that thing has spread, it's only a limited number of hosts. I have 100,000 hosts. I don't have time for 100,000 hosts, but I only talk to 50 hosts. So I only have 50 hosts that I need to add in and begin investigating. That's great. And let's say I find, oh, one of those was affected. Only one out of the 50. What was the type of communication that it had? What protocol was it using? What ports were involved? How much data went by? And I can now profile that and say, okay, from that machine, are there any things it did after that that have that profile? And if the answer is yes, it talked to 100 things, but only one of them, well, that's where they went next. And now I'm rapidly doing incident response. That's great. But that's just the incident response. There's other ways I can use it too. We could be using it for bandwidth and top talkers, which are interesting initial ways of doing threat hunting. But here's another way we could do it, just using data we already have. I've here taken data out of, I forget how many days this is. This is days of data, maybe a month of data, I don't recall, out of a real network. And what I'm plotting is how many packets there were in each time period. And I know the graph is not particularly pretty. It's actually not very useful as it is. But this is a very naive representation of the data. It's just how many packets were there. But this is how we're usually visualizing the data. Because if I go back, that's what's the bandwidth? What's the utilization like? And that's what we're usually looking at. We're using an MRTG-like thing to show what's happening. This is a time-based view of the data. It's time series data, how it happened over time. It is in the time domain, which is how humans usually look at the world. But if you're an electrical engineer or have that training, that's not how you look at the world. You look at the world, I mean, you're a human, so time is involved, but you instead love to look at things in terms of the frequency domain. Now, is there anyone from my class this week here in the room? Okay, I don't think so. I actually told them, don't come tonight. Don't come. I know you wish your instructor told you that. You're like, what? I shouldn't have been here? Because everything that's in this presentation is a thing we teach you how to do in that class. So it would have been a waste of their evening because they're learning how to do all this stuff. Anyway, I'm turning it into the frequency domain. Now, in case you have a statistics background, this is not a histogram view. A histogram is how frequently did things happen? That's not what I'm saying. I'm saying you have data that's a time series, and I'm wondering if there are periodic events that are happening. And I have up at the top here, I'm sorry, it's not on this one. It was on the last one about beaconing. Because when you have malware these days, when you have attackers these days, they tend to be far less direct, which is good. The reason they're less direct is because you know what? We're finally getting better at, there isn't just some exposed service you just compromise and you remotely control my stuff. That's great. Now they have to upload some kind of web backdoor that's going to periodically go out, or the malware is going to create the outbound connection. But if the malware creates a permanent outbound connection, it's not something I'm going to talk about tonight, really, but it turns out that it is not terribly difficult to create an automated detection that says, hey, I want to know if there's any connections that have been up for, let's say, I don't know, more than 5 days. How about that? Because if it's up for more than 5 days, or more than this many bytes have left, or that feels like something we should know about. That's a trivial thing to do. Look at Zeek. It's a trivial thing to do. Those things are easy to find, but malware doesn't do that generally. Instead, what malware does is it's installed, and it's now going to periodically go out and say, do you have anything you want me to do? You have any orders from me? And then it comes back and executes them and returns results. But most of the time, there's nothing for you to do. It's just there, and every so often, it's going to go out and just check. Anything for me to do? And we have a name for that. We call it beaconing. It's beaconing out. Well, what I've done is transform the same data from the last slide into this, which is a frequency domain analysis, which I'm not going to go through the math of it or anything like that. But by making this transformation, I know you can see that there's this huge peak over here at 0, which I'm going to tell you we can completely ignore. And the reason I can ignore it is because the way I'm approaching this is I'm using real valued data to perform the frequency analysis. But the frequency analysis that we do is actually moving things into the complex plane. And as I say complex plane, you're like, okay, I'm tapping out. I'm done for the night. We're not going to do any of that. But because of that, and because I don't have complex data here, I have real value data, I end up with what we call a DC offset, which stands for direct current. And I know, again, you're like, wait, I thought this was network data. Yeah, no, I know it is. We just call it the DC offset. And we call it that because in electrical engineering, we use this to do signals analysis. And when you have a direct current creating an offset in your signal, it will create that. I don't have direct current data here, but I don't have complex data. I don't have phase-oriented data that's going across a complex plane. So I end up with this DC offset. I say all of that to say, I should have just said this at the beginning, we're going to ignore the big spike at 0. It just doesn't matter to us. But then right next to 0, there's, so that's 0. But then right next to 0, there's still a lot of stuff happening. Let me tell you what that says to me as a data science-y person. I look at that and I say, what that means to me is there might be more signals there that are happening more frequently than I can detect with the current sampling rate I'm using. I might need to sample this data more closely so I can zoom in, so I can pull that out like a slinky, right? Just pull it out and say, oh, that all fades away. Because there isn't a coherent signal there. There's just a lot of noise, but all the noise is piled up and it's creating a spike. Or I pull it apart and, oh, there is another spike there. And I have a spike here. Here's a spike. I think we can see that's a spike. That's a spike that's interesting. Sorry, Mike. Come on. There we go. That's a spike that's interesting. That spike is happening once an hour in this data. Again, I'm not going through the math of it, but that's how that works out in that. That's once an hour. And you can see that there's some drift around that, right? There's reasons that happens because I'm telling you, we can detect this thing. I can do this frequency analysis and there it is. So as an attacker, what let me detect that? Well, it was happening periodically, once an hour. So you're an attacker now. What do you do to your malware so I can't find that anymore? I add a jitter. It's no longer every hour. I'm going to add a little randomness back each way, which is actually why using a lower sampling rate, which gives me this pileup at the left, lets me find that thing, because now the bin of frequencies is wide enough that it doesn't matter you jittered, you're still somewhere in that bin. So I still have a spike and find you. So that's why there's some spread there. This immediately, for this network, lights up that there's a beacon happening once an hour. That's interesting. There's an interesting experience outside of this too, because this, I said I teach in the 595 class. And when I taught this in December, wherever the heck that was, I feel like it was Baltimore, maybe, I don't know. I had some guys in that class who were really keen on this part because they had dealt with a lot of malware beaconing and all kinds of stuff in their network. So what they spent some time, they said, so wait, okay, so where'd that come from? NetFlow. Do I have to use NetFlow? No. Any source of data that can give you time series. Well, I've got a firewall. Sure, because your firewall probably is logging at a minimum every failed connection. But if you've just left it at the defaults, it might even be logging all of the successful connections too. All you need to do is, and I'm going to leave that part of the conversation now, because there was some code they had to write to kind of group the data up and prepare it for this. And they came back in the morning and said, hey, can we show you this? Look, overnight, we found 5 more infected machines with beacons that we had no idea existed. And for me, that's why I'm the data science AI ML evangelist, because I don't really care about the theory. I care about how can I use this to make my life better as an operations person for security. And that's useful. Are there attackers I'm not finding? I'm sure there are, because it's like a splinter in my mind driving me crazy. But am I now finding guys that I wasn't finding before? That's what I care about. Am I moving the needle? That's threat hunting for me. I'm not saying I'll find everybody, but I can find some of them. And there are a lot of things that I do. And some of you, if you've taken 503 with me, you know I'm a little on the paranoid side. So I'm building like detection scripts for attacks that don't exist, just in case that ever happened. Now and occasionally you'll get things like that. You're like, oh, it's not what I was looking for, but it's interesting. So let's talk about another one. Here's another data science-y thing. And this is, the last one is just math. This one is really data science. In this case, what we're looking at is an application of clustering, which is a data science, a traditional machine learning data science thing. I've got a tool called Zeek, which I mentioned earlier. Zeek is really great for automating large-scale correlations in an enterprise to feed useful alerts to a SIEM. Though very few people are using it that way. Most people are using it to enrich their logs. And Zeek themselves, well, Zeek is the open source version. The commercial is Corelight. Corelight is the commercial version of Zeek. And this is a weird thing to say. It's not usually how it is, where they have stripped functionality out of the free version and marketed it, which is a what? So the free version gives me more? Yes. And I get why it's happened. It's because they have tried to harden their appliance. I actually got them to ship me an appliance because I went and talked to the Corelight guys at some conference. I don't know, it was before the pandemic, and said, listen, I mean, don't try to sell me your tool, okay? I am not interested. I use Zeek, we use it all the time. I teach it in my class, we use it in all the enterprises. I do not understand why I want your thing. Why would I ever want your thing? And they said, we make Zeek easy. And I said, but Zeek is not hard. So why would I want your thing? So they sent me one. They have gone to an enormous amount of effort to harden that appliance. Now, when I say harden, you're thinking, oh, so there's like no extra ports running. It's like fully patched. It's some custom, maybe it's sent us with like rules and privilege levels. No, 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 you misunderstand me. I mean, the case is all done with security screws, they're tamper evident stickers, you plug a monitor into the thing and turn it on, the BIOS is hardened. You cannot get to that thing. And the reason is because they want to sell these appliances. And if I sell you one of them and you take the drive out and image it, and you could just make your own, and there's no money in that. So what have they stripped out of Zeek? Well, Zeek has its whole own scripting language that is why you can do amazing correlations. They have cut everything out of the scripting language that would ever give you any kind of file system access to the sensor, which I'm sure for the majority of people, they just don't care. But I mean, we do some aggressive scripting in Zeek, and that matters to me. So their tool doesn't work for me. When you power on their sensor, though, their sensor doesn't help we're just going to enrich logs, because nowhere in their documentation for Corelight, nowhere in their, get the thing started is anything about how do I build custom detections for my network. It is turn it on, type in the address of your SIM, and press go. So it is all about sending the rich logs. In this case, for what we're doing here, I'm not doing any advanced scripting. I'm just using those rich logs, but I'm using them instead of just putting them into the SIM. One of the things it actually generates a log for every kind of network activity you have. One of those things is information about every DNS query that has occurred. What the query was, what the response was, everything. It's useful stuff. I want to know if there's any threats in that. If I have a known list of bad domains, that's easy. And there are companies that I can subscribe to. I pay a subscription. They're going to give me those lists. They will curate the list of known bad things. That's fine. But I'm looking for threats. I'm not looking for the known stuff. I'm looking for the unknown stuff. What if we had 1 million unique DNS queries? Now, sure, you've got the list of known bad stuff. Okay, I can filter that out. But now we're left with everything else. Are there any bad things in there in those 1 million queries? Does anyone feel like they want to look at 1 million DNS queries? I don't think I want to look at that, but I'm really interested if there's bad stuff. So let's apply some data science, some machine learning to this thing. What I'm going to do is I'm going to use a technique called dbscan. Now, dbscan, it sounds like it has something to do with databases. It does not. Distance-based spectral clustering of applications with noise. Okay, it's just a lot of words there. We're going to build some clusters on the things. That's what we're going to do. And it doesn't matter if there's noise present. That's what with noise. Doesn't matter if it doesn't matter if there's outliers, just doesn't matter. It won't affect anything, which is not true in most clustering approaches. So when I take that and I now apply it to those 1 million queries, and I need to do something to it to turn that all into numbers, because I'm sorry to tell you this, but data science and machine learning is just math. That's all it is. And it does amazing things, like AlphaGo beats the world champion Go player, but it's just math. And I see people asking on Stack Overflow and other places, so how is that reasoning? Do you get better reasoning when I'm like, dude, it's just math. It's not reasoning. It feels like it is because of how it behaves, but it's not reasoning. It's just math. Anyway, this just math, it takes that stuff and turns it into clusters. And I have here, and I've just done this through, I have a nice graph to put in my thing here because I wouldn't look at it that way myself. But I'm putting this into an R3 or a real valued 3-dimensional space so we can graph it. That's all I'm doing. And that's how the clusters look. And we've got purple things and green things. And I end up with, I don't remember exactly how many. Here it is, 9 clusters. I get 9 clusters out of that. So the million things is reduced to 9 groups. And those 9 groups, they're clustered because they're similar in some way. Tonight for us, it doesn't matter how they're similar. If you really want to know, talk to me at some point. I'll share with you. And in those clusters, I find things like Google telemetry services. They're all like in one cluster. And then there's all the advertising, DoubleClick and all that is all in one. And then there's internal services and stuff, the underscore MSDNS, and those are all in one place. And in amongst these, there's a cluster that has these entries, ZD, ZQ, AA. Now all that stuff is always different. .micro, it's not actually Microsoft, it's micro SOZFT0FT.com. Those are curious looking. Those are Iodine, which is a DNS-based command and control service, a covert channel, actively running on this network. How many things did I have to look at to find that? I have 1 million queries, but how many things did I have to look at to find that? 9. The role of machine learning and data science for me in information security is not, I know there's all this fear, artificial intelligence is going to take people's jobs away. Not in our field. I really don't think so. That's not what it's for, because there's no way I'm trusting machine learning or AI today to defend my network. It's just not there. When you see movies, what you see in movies about AI and machine learning is nowhere near reality. When you read articles about it, they are nowhere near reality. It is just math. I said to you that AI is headed to a bad place. Here's the bad place it's going. In the AI field, we have repeatedly gone through what we call AI winters. If you look back, machine learning and AI has been something man has wanted to do for hundreds, if not thousands of years. And if you look back, there are some phenomenally complex mechanisms that were built. There's one that was very well known that could produce drawings. It was completely mechanized. There was no human involved, and it could draw, produce amazing drawings. It could, I don't remember how many, let's say 5. It could produce 5 different drawings. It couldn't draw anything else because it was just a mechanism, but it was an attempt at machine learning or AI. And of course, there's been a lot of scams along the way, and that's where the problem is. There's a well-known example where there was this machine that could play chess. And it would beat people. It would beat masters. And it turned out, of course, that concealed inside of it, there was a human looking at the board with mirrors manipulating the pieces. That's why it beat you. It wasn't the machine at all. And when people discover that, how much are they willing to invest in further development? Money dries up, right? That's not real. Well, looking at our current times, in the 1950s, there was a lot happening because we now have analog computers heading toward digital computers. We develop languages like a language like Lisp, which this is AI. Lisp, this is it. Lisp processor, look, it's all words. You can build new words. You can have sentences. This is it. We're going to have AI. We were so sure that so much money was spent that we actually built hardware-based Lisp computers. What I mean by that is you didn't turn your computer on and load the Lisp programming language to use it. I mean, that computer implemented Lisp in hardware. That's all it did. Symbolics was the company who manufactured them. Those computers are very valuable today, not because it produced AI, but because Symbolics is gone and we stopped making those computers in the 1960s. They are collector's items. They are rare. We taught people languages like Prolog. This is it, symbolic logic as a language. Look, we can create relations and deduce things in the language, and Was anyone here forced to learn Prolog in college? Anybody? Okay. I'm sorry about that, especially those of you who look like you're younger than me, because when I was in college, I mean, Prolog was still fairly new, but I run into people today who tell me they're being taught Prolog, and I'm like, why? Do they hate you? Or is there some tenured professor who only teaches Prolog, so we have to put students in front of him? If it's being taught to you because you're taking a compiler design and algorithms kind of class, okay, that makes sense. But if it's outside of that context, what are you doing to people? We don't use Prolog because we promised it was AI, but it wasn't. In the 90s, the promise of AI was expert systems. We spent tens to hundreds of millions of dollars in organizations buying these expert systems that promised to be AI. And the way you use them is you take the system and then you take a human, and then you have the human write a lot of rules in some language that will take the data you have and tell you what to do. When did the machine learn? The machine didn't learn. You wrote all the rules. And that was good for like 6 months. But 6 months from now, the basis on which those rules are based has changed. And we need to go rewrite the rules. So there's no real machine learning there. And when companies figure that out, guess what? We stopped buying those things. And there were $0 going into machine learning and AI research. So we've been through this cycle of hype, 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 a lot of money, and then, oh, it doesn't do what you said it does. What are we doing in the field right now? What is every vendor telling you? You need my AI thing. AI is it. Machine learning, that's what you got to have. Would it shock you to discover that some of the vendors who tell you they're selling you AI and machine learning aren't really doing that? Would that surprise you? You heard about the iced tea company that, I don't remember the year, but this iced tea company, they added Bitcoin to their name or blockchain or something. And their stock price went up 500% overnight. Were they now solving blocks in the iced tea cans? No. They just added the word to their name. And that's a lot about where we are in products today. So there's way overhype happening. We can still do useful stuff. Like this one here, we find this iodine command and control. And you might hear that and say, yeah, but look, Microsoft with SO0FT. I mean, couldn't I have found that other ways? Yeah, because if you use iodine by default, it will use that domain name. So that could have been in just a bad list, right? But here's the beautiful thing about what we just did. If you reconfigure that and use any name you want to, and then recluster the data, guess what? Iodine is always in its own cluster. That's useful because it doesn't matter how you reconfigure it, I still find it. And it doesn't matter how many queries there are, it's still in its own cluster. Could there be other covert channels over DNS? There could be, but I found that one. So I'm not solving every problem, but am I getting better? That's what I care about. This idea of finding anomalies is a really important one as well. And that's where we started, right? Find the anomalies. How do I do that? We couldn't do it 20 years ago. We needed a human, but we can do that today. As an example of this, I have some graphs here, and these graphs, I know they're pretty, right? They've got nice colors. It's a nice selection of colors, but what's it mean? What you're looking at here is the application of an autoencoder. Autoencoder. Oh, what's that? The idea of an autoencoder is I'm going to produce some data. So I'm going to build a network, a neural network. So I'm just going to draw some circles and say there is a what? Oh yeah, I know. I'm not worried. It's showing. Yeah, I'm sorry. It's a little dim. I can change colors, but we've got an autoencoder here, and it's going to have a neural network that's got neurons. I'm just going to put circles. Use your imagination for how many there are and pretend they're round. And what I'm going to do is I'm going to take my data and input it. So let's say that I'm going to input a picture. So I'm going to take my little friend Bob here. Bob is going to be in the input. Sorry, I'm not wearing my glasses, so I can't see Bob. Okay, we're going to put Bob's picture in on the left-hand side. And then I'm going to shove that through this autoencoder. And in an autoencoder, it has a particular design. in the autoencoder, what tends to happen is we start out with a lot of neurons and we feed that down into sort of a hourglass on its side. And I've run out of room for the other end of this. And out of the other end of this, so I shove Bob in one end. And if I have trained an autoencoder to find Bobs, then out of the other end of this, I am going to get something Bob-like. Now, it might not be the same Bob I started with, but it's going to be Bob-like. How is that useful? Well, here's how it's useful. This autoencoder knows how to take a Bob and boil that Bob down. This is what that bottleneck does. Boil that Bob down to the most essential things that make him Bob-like. We start out with a lot of features and we push it all the way down. There's almost nothing getting through that middle. Only the most essential things that make that a Bob. And then we spread it back out. And what the other end of that, so this end is called an encoder, and what the other end is called a decoder. It is now trying to take that most essential thing that makes a Bob and turn it back into a Bob. And if I push a Bob in on the left-hand side, and I've trained my autoencoder, I'll get something Bob-like out of the right-hand side. It won't look like the same Bob, but it will be Bob-like. What if I put a cat in the left side? Cats are not very Bob-like. So the encoder is trying to encode that cat, but the encoding it ends up with is not really a Bob-like encoding. So when the decoder tries to reproduce a Bob out of that, what do we get? Not a Bob. We don't get a cat either. I don't know what we get. We get a chair. It does not look like a Bob. How's that useful? Now there's math involved here, but what I can do is I can now measure the reconstruction loss. The reconstruction loss is I gave you a Bob on this end. You gave me something out of the other end. Let's think of it this way. Let's lay them over each other and say, how close are they? Oh, they're pretty close. You know, they're not exactly, but they're close. So I put your cat in on this end and you gave me a chair out of the other end. Those don't really line up very well. They are very distant from each other mathematically. The reconstruction loss is very high. Well, what we're doing here is we're taking that idea, which is a deep learning neural network approach. This is actual machine learning. And we're building autoencoders that identify all of the expected protocols that I expect to find on one of my customer networks. Yes, this is real production stuff out of a production tool we use. And what I'm showing you, the blue line for, let's say, the first one, boot service discovery protocol, the blue line is the reconstruction loss of boot discovery protocol going through the boot discovery protocol autoencoder. It is a low loss. The orange line is anything else. So that's just random network stuff going through it. And what you'll notice is there's some that like dip down, but is it pretty obvious to you that if you look across these, they are more or less linearly separable? In other words, I can draw a line, and while there's some overlap here, generally speaking, there is a line I can draw, and everything that is the thing is below the line, and everything that is not the thing is above the line. Okay, well, that's cool. What do you do with that? Well, if I know everything that's supposed to be there, now, I don't need to know that by going and enumerating them all. I can just load or crack network data for a couple of days and then look through that and say, do we use boot discovery protocol? Oh, we do? Okay, that's fine. I'm not getting any more detailed than that. Do we expect DNS? Oh, we do. Okay, let's let that through. And now I build this thing. I train it. And I have it watch my network. And as connections occur, they're pushed through the series of autoencoders. And the series of autoencoders, every one of them gets to put its hand up and say, oh, I know what that is. If nobody puts their hand up, what's that mean? That doesn't go here. That's an anomaly. Will I sometimes put my hand up and I got it wrong. Yeah. It's not perfect, but you know what? A human's not going to find it all either. I don't care. But am I now going to find things I wasn't finding before? And when somebody turns on that new thing and never got authorization for it, it's going to light up like a Christmas tree because we've never seen that before. Now, how hard is it to add that into something that's okay? Well, that's not hard. I just take a sampling of it and tell it, hey, there's a new thing for you to know. This works. And we can scale this out for almost any kind of problem. It's a really practical approach to doing it. And that's now real machine learning. I want to give you another example, though. And this is why I know he's like, where's the thing you told me you were going to talk about? It's here. What about this one? If you're engaged in an incident response process, so again, there's something happening, I've captured some asset, there's something wrong, you will frequently do things like hashing all of the binaries to see what's known good, what's known bad, and then you've got the don't know what that is. It's not unusual to run malware detection on it, not cleaning it, just identifying what's happening on that machine as their known bad stuff. But which malware will it find? Known malware. And I know you hear that like, well, of course that's what it finds. I mean, this is like, I can find all the known attacks. Can I find unknown malware? Has anyone taken 610, Forensic 610, reverse engineering malware? So it's a very interesting class. It's a really good class. Reverse engineering malware is an intensive process, however. Let's just imagine that on a system that you've captured, there are, tell me what a fair number is. Some of you guys are more into forensics these days than I am. I have not done system forensics in years. Is it safe to say that there are at least 5,000 binaries on a Windows machine today? Is that a safe call, 5,000? Would you say it's over or under that? He's like, it's over. So let's just say 5,000. How long is it going to take you to apply reverse engineering malware techniques to 5,000 binaries? I mean, you can sure find the malware, but that is an intensive job. Even if out of that 5,000, there's only 500 that were just not known binaries, that is still a huge job. What if I told you there's a thing you could do that is about 80% accurate in finding unknown malware? In other words, what if I could take that 500 things down to like 10? There's 10 possible could be malware. Maybe you have time to look at 10 things. You could do that. That sounds useful. Now, am I guaranteeing those things have malware? No. Am I guaranteeing that none of the other things have malware? No. But you're not looking at 500 things now anyway. I'm just giving you a smaller set to look at. I'm making the problem more practical. So let's talk about that a little. Let's try that. Let me move over here and we'll see how this goes because it was very unhappy for a while there. We'll see how my network connection goes because this is not actually on this laptop. It's that guy over there. And what you're looking at here, this is one of the labs actually from the class we're doing down the hall or across the hall over there. So I'm not going to go through and give you all the details here, but we're going to start with some stuff. So there's a bunch of Python here. Is that too small? You guys okay with that? Okay, all right. So we're going to load in some stuff here. I'm going to be using TensorFlow. I'm a TensorFlow fan. Not because TensorFlow is the best thing ever. PyTorch is cool too. But if you want to build a thing that you want to stick into a production pipeline in an enterprise, that's not PyTorch because they just do not currently have the broad support where I can just run it anywhere. They're working on it, but it's why they continue to lag TensorFlow. So TensorFlow, Google initially invested a huge amount in make this work anywhere. So not only can I do it on my Raspberry Pi and do it in my web browser, but I can also do it on most Internet of Things devices. I can do it on my Android. I can do it on my iOS phone. It's just everywhere. So I tend to use TensorFlow for like production level stuff, though I do still use PyTorch for some other things because it's easier for some other things. Anyway, I'm going to load that stuff in, and I'm going to begin this by solving a whole different problem. So this is not a bait and switch. We are headed back to malware, okay? I'm going there. But I'm going to start with a whole different problem because I'm not assuming you've ever seen a neural network work before. What I'm going to start by doing here, I've highlighted this line where I'm loading this MNIST stuff. MNIST, NIST, the National Institute of Standards and Technology, one of the things that they have released is a data set. That data set has a whole bunch of handwritten digits. Now, this is a very old problem. And in fact, if you have watched a YouTube demonstration of machine learning, there are two that you have probably seen. One is either decoding handwritten digits. The other one is classifying movie reviews. And those are the only two things anybody on YouTube seems to know how to do. I'm starting with that because it's familiar and it introduces ideas, but we're then going to transition over and say, but how do I apply that to my problem? Which is where I find the gap to be in machine learning. I find that if you take university classes about AI and machine learning, Stanford has a phenomenal one you can take for free. You will learn how to write your own machine learning library. And you're going to know all the math that makes that work. And when you're all done, you're going to have no idea how to use that to solve a problem. But you've got a library that you wrote. It's great. And then on the other end, you've got all the YouTube tutorials and the Udacity stuff and everything where you're going to be able to classify handwritten digits, but you have no idea how to translate that into information security. One of the amazing things to me is in the course description for Sec 595, I try to say, if you are a data scientist, if you have ever done machine learning before, you should not come to this class. Now, this is the very first time I'm teaching that class where I didn't have a thing happen. Every other time I've taught it, I ask, are any of you have data science training and everything? And like half the class is like, yep, got a data science degree. Like, what are you doing here? And their answer is uniform. Their answer is, I don't know how to apply that to information security. So that's a big issue. So that's why I'm starting with this MNIST thing. It's a familiar, it's an easy thing, and then we're going to translate it. All right, so I've loaded in the data. Let me just split this here and show you what the data is. So the X train, Y train, if I look at the X train data, and forgive me, it's a lot of Python stuff here, but this is just a whole bunch of numbers. And what those numbers are, they are numbers that go with the Y data. The X data is the picture of the digit. The Y data is what that digit is. The X data is where I'm starting. The Y is where I'm going. It's called the target. It's called the label. Depends on which machine learning person or framework you talk to, but it's where you're trying to get to. And you know, we use Y and X for a reason. When you learned algebra and then you learned calculus, now in algebra, you tended to write things Y equals X squared plus 2X minus 4. Y equals. So Y was depending on what X was. X could be anything. Y depended on that. And then you went to calculus and we stopped using Y and we called it F of X and G of X and Z, but it's still Y. That's what this is. The X is the thing I'm putting into the function. The Y is the thing that comes out of the other side. So the X data that I'm putting in is the picture. What I'm hoping to do is determine the function. Don't worry, we're not going to do the math. Find the function that turns that image into a 5. That's what I'm trying to do. So I'm going to load in matplotlib here just to show you what the data is that we're working with. Give it a second here. Okay. So here's what I am given. I am given handwritten digits that look like that. And I want to turn them into classified things. I want to know what those digits actually are. Now, as it turns out, these numbers are not terrible, but as you look at them, there are some that are not amazing. Like, can you see in the next to the last row, I would move my mouse there, but you actually can't see my mouse. Hold on, maybe I can do it over here. So this guy over here, see this 9? Or at least I think it's a 9. Could that also be a 4? I mean, I think it's a 9. So some of these are a little sketchy. This 9 over here on the left, whoops, I went too far. That one looks more like a G to me. I don't know, whatever. So some of them are a little on the sketchy side, but we're going to see how well we can do. That's what they look for. I'm now just going to do a little manipulation on these. That doesn't matter for us. I'm just trying to make the stuff all the right shape and size, because the way this stuff all works, it is all math. It's two particular branches of mathematics that are particularly important here. Multivariate calculus, and I'm not trying to scare you off, okay? You don't have to know these fields, but they're the fields used. Multivariate calculus and linear algebra. To use linear algebra, which is a really important aspect of machine learning and AI today, things have to be of the same size and shape. It's just part of how linear algebra works. It doesn't matter what the size and shape is, but to put them in and get them to work together, they have to be the right size and shape to go together. It's like jigsaw puzzle pieces. So all I'm doing here is just getting things to be good sizes and shapes, making them into matrices and vectors and stuff, all this cool linear algebra stuff. And then I'm going to convert the Y data, which right now is numbers like 0, 1, 2, 3, 4, 5. What I'm doing is converting it into, in fact, let me split this and show you what I've done with it. I'm converting it into, let's look at the first element, into that. So the very first digit is a 5. I used to have a 5 there. I have now made it harder to read. I mean, that's part of my goal in machine learning, right? Make it hard and intractable for people. But what I've done is made it easier for the machine, because it is now in position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So only one of these is on. There's a name for this. It's called one hot encoded. What I'm doing is indicating which digit is it. Now, for your mental picture, what's going to happen in this in the end is I'm going to push it through a neural network. Remember those circles I had before? I'm going to push it through a neural network. The X goes in the neural network, and on the outside of the neural network, there will be 10 neurons. The first neuron represents 0, then 1, then 2, then 3, then 4. And after I push the image through, I want to see which one of those neurons is turned on, or because they're probably all a little turned on, you know, but the most turned on. Which one has the greatest activation? And that's going to tell me which digit it is. I know it feels like that shouldn't work or anything. That's just like black magic. But let's see what happens here. All right, so that's what the data looks like. Now I'm going to build the network. And I'm sorry, you are not my machine learning class, so I'm not going to explain any of what all of this is doing. But I'm building a thing called a convolutional neural network. The convolutional neural network is a relatively recent development in the AI and machine learning world, and is incredibly useful in computer vision tasks. And that's what this is. Look at the number and tell me what it is. I can actually solve this same problem using a more traditional neural network, a dense neural network, which means no convolutions. It's just shoving it through the network. In the convolutional neural network, what it's doing is looking at little pieces of the image, and it's just convolving, going across each of those lots of times to build some other representation of the image. That's what a convolutional network does. Convolutional networks are amazingly powerful because of how they look at the data. And it ends up that once I understand how to look at a thing, it doesn't matter if we rotate it or move it, or because the convolutional network doesn't really care where it is in the image. It's looking for the characteristics that make that thing up. Where a more traditional network, just a regular dense, just network, just neurons connected together. I can find zeros, man. I can identify all the digits, but if we move the digit, it can't find it anymore because it's not where it thinks it should be. They're very powerful things. They're very cool. So I'm building one of these things here. I'm building a convolutional neural network that's going to have kernels or filters that are 2 by 2 pixels, not very big, and that have 8 of those filters at a time. So it's going to develop 8 different ways of looking at the data. And then I'm just going to push that through a traditional neural network. Don't worry about any of the other, parameters or anything. I mean, it matters. It doesn't matter for us. Let's then train that model. Give it a second, off it goes, train, train, train. And you can see here the accuracy. So at this point, it is already at over 80% accuracy. It is only one pass through the data. It's at 94% accuracy at this point. And I'm tracking a loss value. How wrong am I? which is not the same as accuracy. It's how far off am I versus the accuracy. How often am I getting this right? And there's two accuracy numbers I'm producing. This is the accuracy value. I keep forgetting you can't see my mouse. This is the accuracy value looking at the training data. And then there's other data that it's not using for training. It's just using that data to validate how well the training is going. Because if I keep running the same data through it, it can begin to kind of it's like memorizing the training data, and it's not really learning anymore. But I can see in my validation is 97%. I mean, that's pretty darn good. I mean, that sounds promising. Let's ask it to evaluate that. Now this evaluate, I'm passing in my test data. It has never seen these handwritten digits before, along with my answers. Here are the right answers. And it tells me that is, I know it says 0.97, but it's a percentage, 97%, which matches the training. In other words, it is now able to look at handwritten digits, and 97, 98% of the time, it can get that digit right. Can't a human do better than that? Because remember, these are handwritten digits. Some of these digits, man, they are really sketchy. None of those really showed up. There's, I think, 10,000 of these things. None of them showed up in the samples I showed you, but I'm telling you, some of them are sketchy, and you're going to get them wrong. But I'm not sure I need perfection out of machine learning. I know we expect it from machines, but we don't expect it from humans, do we? So as long as it's good enough. In fact, I asked you at the beginning, I said, so if I could give you something that can look at a set of files and tell you 80% accuracy, whether or not there's unknown malware in that, would that be useful? And you're like, oh yeah, that'd be useful because I can't find it at all now, but it's not perfect. And you're like, well, that's okay. So really, it doesn't have to be perfect because it's making the human's job easier. If you're right 97% of the time, I'm happy to pick up the slack on the other 3% because I can go and get a cup of coffee while you do that. So that's fine with me. Anyway, just for a little completeness about what's happening under the hood here, I'm not going to explain these things, but I want to show you how it's working. I said to you that I'm building or using 8 filters or 8 kernels. And I said those kernels are 2 by 2. 2 pixels by 2 pixels. Here they are. These are the trained. I'd like to introduce you to the stars of the show, the things that have actually identified the digits, and they are not very impressive at all. What I'm visualizing here is how active or how turned on each one of the individual pixels are in those filters. And there's nothing interesting there. What's happened is that these started out as random values, and I know they might look random now, but they're not. They started out as random values, and then it iteratively trained and did some cool math to figure out how to adjust these to better identify those digits. And in the process of doing that, here is what it has worked out. When it looks at one of the numbers, here is how those 8 filters see the number 7. Each filter, well, I mean, some of the filters end up doing the same thing. How many filters do I need to identify digits? I don't know. I know that may not sound cool. Did you have math teachers who you asked them, so what's the right way to do that? And they're like, I don't know. Was that something you often heard in math class? Probably not, right? Because we unfortunately teach people that math is all about rules. You need to follow these rules, and that's how you solve the problem. And you don't find out until like after multivariate calculus, you find out, oh, we've been lying to you all these years. What happens is we have a problem. We're like, well, let's try that. Oh, that's interesting. That looks like, yeah, I think that's the way to do that. That's where that comes from. And then we end up like proving that works. And now we have a new rule, which isn't how we teach math. I don't know how many filters will solve this problem. I have no idea. And currently today, there is no known way to know deterministically how many filters you need. So what I do is, I think I could probably do it with 8. Let's try 8. And let's make them, I don't know, 2 by 2. Let's see how that works. And if I get, oh, I'm 97%, I'm happy with that. Could I get it to 98%? I don't know, maybe. I mean, do you want to try like 3? Maybe we'll do 15 filters. I don't know. And I'm sorry, that is the reality of how AI and machine learning is built. If you want to watch a really interesting documentary, it's not very technical, okay? So don't watch it for that. But a really interesting documentary, watch the YouTube documentary from the AlphaGo team called AlphaGo. And one of the most amazing pieces of that is while it is playing the Grandmaster and AlphaGo makes a move where like all of the, I mean, I think it's won 2 games so far. And it makes a move and the grand champion is like, did you see that? And the commentator's like, oh, it's made a big mistake. What's it doing? No one would ever do that. And the AlphaGo people, you see them in their control room, like, what happened? What's it doing? How did it make that decision? Where'd that come from? Is there something wrong? Because it's a baffling choice that it makes. It actually goes on to win that game. But the people who created have no idea how it came up with that choice. And those people know AI way better than I do. I promise you. There is no known way to know what the right answer is. So I picked 8 and I end up with a couple, like I'm looking at the bottom left corner here. It looks like they're looking at the same thing and they're finding the shape of the 7. Others are looking at different things. Some are finding horizontal lines, some are finding diagonal lines. I have no idea what the guy in the bottom right corner is. I actually think he's kind of taking the day off. And that happens in neural networks. You end up with neurons that don't actually contribute to the process. There's a whole field of research on how to prune AI networks to make them more efficient and get rid of the dead neurons. Anyway, here it is just looking at some different data. And you can see that the different filters are highlighting different things. They're finding different aspects of the numbers. Okay, let me get where this ends. So that's cool. But you said we're going to talk about malware. Okay, let's do that. The reason that I do that introduction, oh, did I just, what's going on with my network connection here? Hello? Oh, it moved, okay. In order to solve my malware problem, I am going to do a thing that makes absolutely no sense. Because when I say we're going to do some zero-day malware detection, you're like, ooh, so you're like, are you automating the reverse engineering thing? Are you training a neural network to understand machine language and derive what DLL calls are happening? No. I mean, that all sounds very cool, but it sounds hard. I'm not doing that. What I'm going to do is say, I wonder what would happen if I just, for the sake of argument said, let me treat the binary as though it were image data. I mean, I know it's not an image, but let me just treat it that way. Because if I do that, I know about CNNs, right? And I wonder if anything interesting would happen there. One of the things I talk about in my class, I tell them in class that there are a couple of labs in the class that don't work. And I explain to them, when I say don't work, I don't mean it doesn't run. It runs. I mean, all the code works, that happens. But the result is like, nah, it's not useful. And I've included that because otherwise you leave that class feeling like, wow, this is easy. I mean, I can solve any problem with this. And that's just not the reality. There are hundreds of experiments you're going to do and things you're going to try that none of them work. And then you do something like, oh, well, that's good. But what do you hear about in presentations and what do people write about in blog articles and doing in keynotes and stuff like that? They don't tell you about the stuff that didn't work. They tell you about the cool thing they did that worked. So don't feel like this is just automatic, right? This was I wonder what would happen. This actually is someone else's paper. I read a paper about this and they said this worked. And I'm like, oh, okay, that didn't work. There's no way that worked. I think they made the data up. Because they just need to get their degree. They don't really care. They're just writing a paper. I think they just made the thing up. I don't think that works. I want to see if that works or not. So I tried it out. And you know what? It works. So let's try the thing out. So what I have done is I have a bunch of data here. This is how I got the data. I am going to arbitrarily choose to look at a 128 by 128 block of bytes. So 128 squared. That's how much data I'm looking at. That is just an arbitrary choice. And I'm defining it in that way, which is a weird way to explain it when I'm talking about loading bytes, because I'm thinking about it as an image. So it's a square of data. So that's the top and the side edge. That's how big the thing is. So the total size will be whatever that is. And I don't actually know that number offhand. So let's just see how many bytes that is. So it's going to be 16K. I'm going to take 16K out of the file. That's it. I have actually pre-built this, and this is less for the demo, right? This is for my class, because for my class, I'm distributing them all this data. How cool would it be for me to hand them? Did I load it here? No, I didn't load it here. Oh, this is plotting that stuff out. Let me do that. How cool would it be for me to hand them a USB stick or get them to download, I don't know, 40 gigabytes of malware? Everyone's cool with that, right? That's no problem. That's not going to be awesome, right? People are going to make mistakes. People are going to mishandle stuff. It's nothing to do with malware. You want to hear a funny story? So my son and daughter-in-law, we built a house on the back of our property for them. Don't mishear that. It's like we're like out in the country. Okay, it's a small house, and we just wanted them around because we feel like grandchildren are in the near future. So we lured them in with a house, and my son, he's in his 30s now, but when he was in his 20s, he had this fascination with swords, and it actually started when he was a teenager. I'm sure many people can relate to that. He loved swords. So he had this sword, which was, there's no way anyone ever used a sword this size. It was just enormous. He's like 6'2", and the sword was taller than him. It was just huge. And he texts us or comes by, I can't remember, and he's like, oh man, look what I did to my foot. And he has sliced the whole bottom of his foot open. I think he needed stitches, but he didn't go. And we're like, what happened to you? He's like, I stepped on the sword. It's like, what? How'd that happen? And his wife, she is the most adorable thing. She's like 5'2". She's like an elf next to him. We're like, what? We're looking at her like, what happened? She's like, I've been telling him for months he needs to take that thing off the floor. He doesn't listen to me. I'm not moving it. So he stepped on the sword, and she's like, good for him. It's awesome. Anyway, here I've got these images. These images are not very interesting because what I've done is taken 16K of data out of binaries. These are good binaries. I can tell. Can you tell they're good binaries? I know they're good binaries because I just loaded the data. These are just known good binaries, just operating system files off of Windows. That's all these are. And I don't remember how many there are. There's thousands of them in there. And I've chosen to represent them as an image. And they look like, if you are old enough to remember snow on your television screen, that's kind of what they look like, right? It's like the vertical hold is off. There's something not right. Let me scroll down a bit more. So there's those. Now I'm going to load the malware. So for the class, what I did is I didn't want to hand them the malware because I just could tell that was not going to turn out well. So all I did was pre-process it and extracted just a certain number of bytes and put them in a NumPy array that I saved. So they could just load the data back up. But it's like we just read it out of the files. Here I am looking at the malware. Can you tell? Not really. Okay, that's all right. But they are now images. So what I'm going to do is I am going to reshape that stuff, do some Python magic with that to turn it into things I can push through my neural network. And I am then going to build a neural network. Now, this neural network is a little more complex than the other one. Why? Because I felt like it should be. That's it. I said, let's just, I'm going to start with 8 filters and then do 16 and then do 32, which is a pretty typical approach in convolutional networks. You start with a smaller number and have more and more as it finds more detailed features. That's what we say knowingly say to people, because then it can find more details in the image. I don't know if it really does that, but that's what we say it does. And I'm going to make those kernels bigger and bigger, so it's looking at bigger and bigger regions. I don't know. I'm just going to try it. And I'm going to push that out. There's my network. And now let's train it. Train. Now, do not expect 97% accuracy here, okay? Because think about what we're doing. I'm saying, let's look at the binary as an image and see if I can tell it's malware when I do that. But I'm already over 80%. But remember, we are looking at the training data. So it's looking at the training data multiple times, working out a way to determine this. And it ends up saying that, oh, my training accuracy is 93%. Wow. I don't know if I can trust that. The validation accuracy was 83%. That's still pretty good. But let's instead have it look at malware it has never seen before. Oh, and this is, I'm sorry, it's not just malware. Half of this is malware, half of it is not malware. And let's see how well it identifies that. 88%. Now, I said in the slide, better than 80%. It turns out, and I'm not more specific about it, because when you train these networks, the math is too complex. We don't know what the best network is that will do that. And since we don't know, and since the error surface is vastly complex, there's no way to know where to start. So we start the training, it initializes it, I actually said this earlier, to random values. And then it tries to improve from there. So in this particular run, I now have a network that with this test data is 88% accurate, which is pretty impressive. I don't think I've ever gotten a number lower than 81 or so, but this tells me there's still room for improvement on this. Does this approach have legs? Because if I can now, at an 88% accuracy, say not malware, malware, I'm dramatically reducing the number of things I need to investigate. But I'm also adding things to investigate, because I now have a way to vet them and say, take those 15 things and let's go do some reverse engineering on those things. And I'm not telling you that they're all malware, but there are signs. What are the signs? I don't want to tell you. I consulted a psychic. I mean, that's what we've done, right? I'm not going to tell you, but there are indications. One of the big things these days, one of the things people are very interested in is the notion of explainable AI. Explainable AI is, remember the AlphaGo guys? Why did it do that? Is it broken? Did something crash? That's not explainable AI. They are trying to explain it and they don't know why it did it. Explainable AI is sort of like, remember that thing I said where here's what the filters look like and here's how the filters look at it? And see, it finds the line in the 7, it finds the hard. That's explainable AI. Convolutional networks are really good for that because they're visual, but most other networks are not. Why did it do that? I don't know. But that's what it did and it worked. Why is this working? I don't know, but I can theorize. Those of you who have done malware reversing, will you agree with this? While all malware code is not the same, there are characteristics that malware code tends to have. There are ways you write it. There are instructions you use. There are patterns in the way you use them. And because of that, we end up with features that are recognizable. And they're not, I mean, in the code, they're not visual features, but when we represent it visually in pixel intensities, it ends up becoming apparent and we can spot them. I don't know what the features are. I don't really care. I mean, if I really wanted to, could I do more research with this and say, well, what are the things that it's looking at that's telling it that's probably malware? Could I build something? Probably. I'm just not doing that research. I'm in a different kind of place with that. I'm interested in things that I can apply that are going to help direct me toward finding threats in my network. I am not primarily a malware researcher, but wow, that's handy for me for IR and threat hunting. So where we are today is that we have a lot of tools that were being sold. And the vendors are saying, you need to buy my AI and my machine learning stuff. I don't know of a vendor. If there is one, tell me. I don't know of a vendor who's saying, I've got an AI thing you can run that's going to tell you about unknown malware on your network. 0 days. I don't know anybody doing that. There are companies that are selling AI and machine learning stuff and telling me, what you need to do is set this up on the network and let it run for 6 months. And then you're going to start to get some interesting results out of it. And I hear that and say, that's not useful for me. I don't need to know what the threats are 6 months from now. I need to know what they are today. And worse, I have a different fundamental problem with that. So it's going to run on my network for 6 months and then start telling me about anomalous stuff. How long are people compromised before they figure it out? Oh, it's more than 6 months. Yahoo, 4 years. I mean, so if I set that thing up and let it run for 6 months, is it going to tell me about the things I've got now? Or is it going to tell me about the new things after that? I need to know what I have now, which is why I approach it the way I do, where that network auto encoder and the other identifications that the other things we do in 595 come from. I need to find threats now. I'm much more interested in the anomalies. That's where I come from. How can you do that if you want to? Well, what I've talked about with you here does not require you to go buy any tools. You don't have to go to talk to any vendors. This requires you to go and educate yourself. So you are welcome to do that. Go and do the research. It's all out there. If you went to college and took calculus, go get that calculus book out and dust it off and learn about partial differentials again, because you can implement all of these things. And it's not that you have to go and do it at that level, but there's a huge value in having a basic understanding, a familiarity with what the map is, so you know how to reach into the toolbox to get the right tool to use. Because otherwise, you've got a whole bunch of tools and you don't know what they do. And you're just going to take each tool and try it with your problem and see if you find the one that works. And that doesn't work for me. What we do in 595, and that's the alternative, right? Go and do it yourself. I mean, help yourself. But in 595, what we've done is try to give you here are the essential things about how and why that works. So when you now have a problem, you say, oh, I need to do, this is a multi-class classification problem. So I need to reach in, I need the